Welcome back to the Professor's Du Bois channel. I'm Professor Victoria and this is Professor Corey, and today we're going to be talking about how to prepare solutions of known concentration. We learned about molarity in our last video, and that is a concentration unit for solutions, and we've learned about how to create that and how to make that molarity from mass, volume, in different concentrations. And today we're going to learn how to use two different methods to create a solution of known concentration.
And we made a note here that this is probably the most important lab skill, because if you're working in a lab, you're likely going to be doing this every single day. And there's some stuff we kind of have to go over before we get started, I think, in terms of glassware, because when we want to make a solution and we want to know that concentration, the exact concentration, we have to be very specific with the glassware that we use. And so a solution, we're making solutions in water, aqueous solutions. We could make a solution in a blue bucket. Absolutely, it would work. But to have the known concentration, we'd have to know the exact volume and the number of moles in there, right? Molarity, mole per liter. And these buckets aren't very accurate. That's probably a 1 gallon bucket or something. It's just not going to work. Take a look at our beaker. You're probably familiar with a beaker. That's over here on the left-hand side. The beaker has graduated lines on here. So unlike the bucket, we could actually add a volume in there and measure it. But as it turns out, these lines aren't very accurate. They're
approximate.
They're very approximate. And the way they post them on there, they almost look like authoritative.
They're close, but they're, not close enough.
Not that close. Looking down at the Erlenmeyer flask, it's kind of like a beaker and the neck gets small. Now this is a great flask for having a reaction in because that narrow neck keeps things from splashing out. It's easy to hold in your hand and swirl and view. Great piece of glassware. Has those graduated lines, also not very accurate. You don't want to use these for measuring. The graduated cylinder, way on the right, we've used these in our lab simulations. These are pretty good, much better than a beaker or a flask, but we can do even better. So if we are going to measure a volume, rather than use a graduated cylinder, if we wanted a very exact concentration, we would use a tool called a pipette. And this is the pipette here, and these come in various sizes. I've seen 1/2 mil pipettes. I've seen 100 mil pipettes. And they make a mechanism that will draw the liquid up into the pipette. There's a line on the pipette that's calibrated to deliver the volume that's marked on the pipette. So maybe this is a 10 ml pipette. If you get the solution to that line, and this takes a little skill, it will deliver exactly 10 mils. The other piece of glassware we might use, if we're gonna weigh a solid and make up a solution and we need to know an exact volume, is this
volumetric
flask. I keep wanting to say graduated cylinder. I don't know why. It's a volumetric flask. Notice it's marked 250 mils. There's a line on this. These are very accurate pieces of glassware, very expensive pieces of glassware as well, but that will contain exactly 250 mils.
The first way that we can make a standard solution, we call it standard, of known concentration, is this direct addition. So we're going to add directly an amount of solid that we need for the volume that we're looking for. So here's our volumetric flask, and here's our graduation mark there. So if we weigh out an exact amount of solid and put it into our volumetric flask, add water up to this line, and you can see this line here quite well. So we have our meniscus, the bottom of our meniscus right on that line. It contains now an exact volume. Let's say this is a 250 milliliter volumetric flask. It contains that exact amount, and we know the number of moles that went in there. So moles per liter is molarity, right? If we know the moles in our solid and we know the liters of our flask, we have a known concentration.
The real challenge there for chemists is getting all of that solid into that flask, because the neck is pretty skinny. So sometimes you'll use a funnel. Sometimes you'll weigh the solid onto a piece of weighing paper, which can be folded up and you can pour into the flask.
Yep, and we call that analytical transfer, where we have to have all of the molecules and atoms into that flask.
So here's a word problem. You'll see stuff like this, and it's really this direct addition method that we just talked about. And what they're asking is, well, how many grams of NaOH do we need to prepare 500 mils of a 5 molar solution? So we're going to use a 500 mil. I wanted to say graduated cylinder again.
Isn't that funny?
It's volumetric flask. We're going to use a 500 mil volumetric flask. We got that. We need to be 5 molar. Okay. So how much sodium hydroxide do we use? And this is it's a tough question. And lab chemists do this daily. So for them, it's not so tough. Here's a couple tips. Look in these word problems for factors. And there's actually quite a few. One of them is molarity. We know the molarity, and even though it's just a big M here, we know molarity is mole per liter. That's a factor. So we want to make 5 moles in 1 liter. So how do we get to moles from a mass? Well, we have the formula, it's sodium hydroxide. We can use the periodic table to get the molar mass of 1 mole. There's another factor. And we're also in milliliters here, and we can use the factor of 1,000 milliliters equals 1 liter, and that's going to help us with the molarity step. So pull out the factors, and let's start this problem with the thing that's not a factor. And the thing that's not a factor is usually a measurement. It's usually a mass or a volume. In this case, it's a volume. It's 500 mils. So I'm going to convert that to liters and then use molarity, the mole per liter, to get to moles. From moles, I can use the molar mass to get to the grams needed.
So just to recap here, you find your hidden factors, right? So that capital M, change it right to moles per liter right away. So you know that you can use it as a factor. If you have a formula, you always have the molar mass because you'll always have your periodic table. And of course, you'll always have your metric units to convert between like milliliters and liters. So once your moles are gone, you can solve for your grams. So if we put that 100 grams in a 500 milliliter volumetric flask and bring it up to the line, we would have a 5 molar solution. All right, here's the second way. So another way that you can make a solution of known concentration is if you already have a concentrated solution, you can dilute it. You don't have to always go from a mass. So if we have a flask that has a concentrated solution in it, we can take a portion of it out and put it into a new flask of known volume, and we'll have a small amount of this concentrated solution. And if we know how much we put in here, we know how many moles are in here. And if we just add water and bring it up to the line, then we have a known volume as well, and we can calculate a new concentration.
And this is where we'd use the pipette. We would use that pipette to take the concentrated, and we'd have an exact volume in milliliters, and then we could use that volume to figure out how many moles there were.
Right. Here's an example problem. So if we have 60 milliliters of a 0.25 molar hydrochloric acid solution, and we take that 60 milliliters out with a pipette and put it into a new flask with a new volume, 500 milliliters, what is the concentration of that diluted solution? And we're going to show you a couple different ways to solve that. What is interesting and what's important in this is that the moles that you remove, the moles of HCl that you remove from the first flask, is the same as the moles that you put into the new one. So how many moles did we remove? We had 60 milliliters of a 0.25 molar hydrochloric acid. So I'm going to solve that for how many moles I removed. So milliliters to liters, and then use your molarity. This is moles per liter. We changed capital M into moles per liter. So now we can cancel liters, and now this is how many moles were removed from that concentrated flask. If we divide that by our new volume, we have the molarity of our diluted solution, and you want to make sure that your diluted molarity is less than what your concentrated molarity was, which in this case it is. And we're going to show you another example of that as well. well, it asks a little bit different question, but
yeah. So what makes these questions kind of hard is, in that one we had 2 volumes, and it's difficult. Where do I start? In this one, we've got 2 molarities, and so we've got a concentrated, that's the bigger molarity, the 15.8 nitric acid, and we want to make 250 mils of a 6 molar solution. So how this would happen in the lab is you'd have to make the 250 mils of 6 molar. You'd go into the stock room and you'd hope that someone already made it, and all you can find is the 15.8 molar. So you're going to be like, okay, I got to dilute this up so that it's 6 molar in a 250 mil flask. So if I start with that 250 mils and convert that to liters, and then I use the molarity of what I'm looking for, that's the 6 mole per liter, I can figure out how many moles I need. That's how many moles of HNO3 I need. So I can take that and use the molarity of the concentrated. Now, this is the molarity. It looks a little funny because it's flipped, but we can do that with a factor. I just want moles to cancel. So I can use that to get to liters, and then I would want to go to milliliters, which is 94.9. Now this is a little tricky. You're probably not going to find a pipette that reads 94.9 mils. So in this case, we would use a graduated cylinder.
We'd have to.
And that would be okay.
All right, so this is kind of complex, this type of calculation. So we're going to also show you kind of a little formula here. M1V1 equals M2V2. And this can only be used for dilutions. Okay, you're going to want to use it for everything else, but you can only use it for dilutions because it'll mess you up if you do it with anything else. So in this case, we have on one side is our concentrated and the other side is our dilute. Doesn't matter which side you use for which. Molarity times volume equals moles, right? Molarity times equals molarity times volume, which is moles, where we said we take the moles of what we take for our concentrated equals the moles that we put into our dilute. That's why this works. You can use any unit for volume as long as they're the same. Mathematically, you can figure that out. How if we divide both sides by 1,000, it's the same thing. So we can have liters over here or milliliters. So in this case, we would have concentrated on one side. So this would be my 15.8 molar times the volume that I want to remove. That's what I'm solving for. And my new volume is 6 molar.
That's your new concentration.
My diluted one. And my volume was 250 milliliters. Now, if I use milliliters over here, when I solve for volume, that will also be in milliliters. So you should try to calculate this out and make sure that you can get 94.9 milliliters. You can use either way.
So you want to get that volume by itself. We'll leave it on the left-hand side. Multiply the two numbers on the right and then divide.
All right. So determining molarity, this is kind of a direct addition, but you already have the amount in grams. So in this case, it's saying if I take that 4 grams and put it into a 250 milliliter volumetric flask, what would be my molarity? And this is a little bit more straightforward. Since we're looking for molarity, we need moles of solute and we need the total volume. So up top here, we have the 4 grams using our molar mass. We'll convert that to moles. Take our 250 milliliters and convert that to liters and simply divide. All right, here's some practice problems for you. Pause the video and give them a shot. We have a couple different direct additions and then also a dilution.
We expect these to be challenging for you, and especially when you're getting started. But like everything in chemistry, if you practice, you will do well. You'll be able to figure these out.
Give it a try. Okay, here's your answers. Hopefully you did well. And we're so glad that you joined us. Thank you so much for watching. We'll be back with more chemistry on the Professor Du Bois channel.